So up to this point, we've been dealing with derivatives as numbers. The derivative is the slope of the tangent line. So the answer to a derivative primarily at this point has been a number. The slope at 5 is 2. But of course, if you remember last year, we took derivatives of equations and we got another equation. So we're going to come up with the derivative not as a number, but also as a function. Our good old limit of the difference quotient. This is a slightly different version of it. The book's version, instead of using an x, they use an a in there. And this is finding the slope at a. That's a number. When you replace the a with the x, which is what we did last year, that's where you get the derivative being a function as opposed to a number. But if you remember what we did last year, and this is, again, ahead of where we are in this book, but we talked about this last year, when you take the derivative of the function 3x squared plus 2x, remember the exponent multiplies down front, that's where the 6 comes from, and then the exponent gets smaller by 1. This exponent multiplies down front, and then you get x to the 0 power, and of course x to the 0 power, x to the 0 power is just 1, and that's why this just becomes then a 2 right there. So think about the derivative. The derivative is a function. The derivative is also a number. It's kind of both things at the same time. Let's take a look for a moment and talk about the derivative as numbers. So I've got a graph of f of x, and a real key thing that I want to emphasize here is f of x. Anytime you see a graph, make sure you are looking at what the graph is a graph of. This is the graph of the function f, not the derivative. Sometimes they'll do that to you. They'll say, here's the graph of f prime. Well, if you are looking at that graph and thinking that it's really f instead of f prime, it's going to totally mess you up. They're different things. So given a graph of f of x, I want to find the graph of the derivative. I want to find f prime. Well, a couple of key things in this graph. Those 2 points are kind of the key points because, of course, what's happening at that point is the tangent line looks like that. And so the derivative has a y value of 0. So listen to this statement. The derivative, sorry, let me say it again. The derivative of the function is the y value of the derivative. The slope of the function, the derivative, the slope of the function is the y value of the derivative. So the slope right here is 0, and so the y value of the derivative's graph is 0. Look what happens if I go in between. All of these points in between, from here to here, those have positive slopes. Everywhere in there, the slope is positive. So look at what the derivative's graph looks like. I have positive y values. Outside of that, over in this region, you've got a negative slope. And as you move over farther, you get more negative. And as you move over farther, you get more negative. And so the y values get more and more negative over here. Whereas, on the other hand, on this side over here, when you were at 0, there's 0. But as you move to the left with that point, those slopes are also negative. So the y values on the other side are also negative values. So the green graph is the graph of the derivative of f of x. That's what it looks like. Again, emphasize this point. The derivative is the slope of f of x. Same problem. Find the derivative of this graph. Graph the derivative of it. those are the key points, because at those points, the derivatives y values are equal to 0. Now look at the first connection, or the first side over here. Everywhere over here, these slopes are positive. So the y value over here is going to be positive. In between these 2 points, these are negative slopes. And so you're going to have negative y values. So the final graph is going to look something kind of like this. Positive slopes over here, so positive y values. Negative slopes in here, so negative y values. Positive slopes here, so positive y values. 0, so back to 0. And then negative slopes here, so negative values. So the final graph, let me do it in a little different color so it's easier to see. Final graph looks like that. That's the graph of the derivative. So graph this thing on your calculator. Pause here for a second and see what it looks like. Should look something kind of like that. Now let's think about what the derivative looks like. Let's find the derivative and see what we can, if we can compare that to that. If you remember how we did this back last year, the exponent comes down front, so the 3 comes down front, that gets smaller by 1. The 2 comes down front, that gets smaller by 1. That's the derivative. Graph that on the same graph. So put that into y sub 2. So compare what's going on. Now remember, the green graph was the first original graph. That was f. We do that in green. This is f of x. And the purple to me, but we'll use blue, is f prime of x. So look at the green graph. The green graph has a horizontal tangent right at that point. And sure enough, the blue graph has a 0 at that point. The green graph has a, right at this point, horizontal tangent. And sure enough, the blue graph has a 0 at that point. In between, green is negative, and so the purple one is negative. To the right, the slope is positive, so the purple one has positive values. Yep, that's it. So just a quick reminder, this is the limit of the difference quotient. That's how we're finding the derivative. We're going to use that to find derivatives of functions to get that. Eventually, we're going to remind ourselves about the shortcuts that come. This is just a little piece on notation. There's lots of different ways to write the derivative. We write it using the f prime notation, but f of x means y, so you can have y prime. The derivative, of course, is the change in y over change in x. Sometimes it's the change in the function over the change in the x. You can do it that way. Sometimes they separate this dx off. So this is saying take the derivative of f of x. Sometimes they abbreviate that and say the derivative of f of x. Very rarely will you see this. It's talking about that actually is a multivariable kind of thing where you'll take the derivative with respect to x. These 3 are the ones we will use mainly in this year. The rest of them, kind of tuck them in the back of your head somewhere. This one may come up again, but mostly the 3. In the book, there's a couple of definitions that you need to take a look at and read. The first one talks about, and let me open up my book here real quickly. I'm going to pause you for a second. So definition 3 on 126, that's the page, by the way. It talks about a function being differentiable at a if f prime of a exists. It's differentiable on an open interval. And they talk about an open interval, a to b, because this doesn't include the endpoint. And the idea there is the derivative is a limit. It's a two-sided limit, and so they want to make sure when you're talking about taking the derivative at a, if I don't include a in the endpoint, that means there's still some room left to the on both sides of a, and so I can have a two-sided limit. So simply what that's saying is, if it's differentiable on an open interval, it's differentiable at every number on that interval. 4, sorry, getting ahead of myself here. 4 says that if it's differentiable at a, then it's continuous at a. So if I have some function and it's differentiable at a, it's got to be continuous at a. Now the reverse is not necessarily true. There are some places where something can fail to be differentiable and it still be continuous. For example, absolute value of x. Absolute value of x, if you remember, looks like this. And it's continuous everywhere, but it fails to be differentiable because the limit, the idea of the differentiability for the derivative is the slopes are approaching the same value from both sides. Well, this slope is always positive 1, this slope is always negative 1 until that moment they meet. There is no approaching each other. So this one would be continuous at that point, but it's not differentiable at that point. This is not differentiable even though it's defined everywhere because the limit doesn't exist. And here it's not differentiable because you have a vertical tangent line. The derivative, of course, of a vertical line is undefined, so the derivative is undefined there. That's it. Take a look at the homework. We'll work on that later. So, by the way, brownie points if you come in tomorrow and give me a high five.